So now we get to a class of functions where the number of inputs matches exactly the number of outputs. If it's 2 or more, then we're not going to be able, if the number of inputs and outputs are the same and it's 2 or more, then we're not going to be able to see the graph, right? So we can't see the graph, and the reason is because that would take too many dimensions to see the inputs and outputs together. But there are 2 ways that you can think about functions of this type, and which one you think of depends on what the application is. We've seen a function of this sort. If you think about the transformation that takes you from polar to Cartesian, we have these 2 equations. X is r cosine theta and y is r sine theta. Can you see how this is really a function? So there's an output that consists of a list of 2 numbers, x and y, and those are given by 2 inputs, r and theta. So we could call this a function. A lot of times we'll use a bold name for it because it is a vector valued function. It's a vector valued function of a vector. So this is a function of r and theta. Remember, this transformation, we could look at it from the point of view of here's the input plane, right, the r theta plane, and then here's the output plane, the usual Cartesian plane. And what's happening is each point in this plane is being turned into a point in the other plane. This is a transformation of the plane. So transformation, we can visualize it. If we think about a line here, a vertical line, that's a line where r is constant, right, in the r theta plane, and those vertical lines just become circles, right? So on the other hand, a horizontal line, that would be a line of constant theta. So now the angle is a constant. Each of these lines becomes a line through the origin. So for each different value of theta, we get a different line through the origin. Apparently I'm not able to go through the origin, but that's my fault, not the fault of the transformation. That's one way, one visualization that comes along with functions with as many inputs as outputs is as transformations. Another way would be, you could think about it if you have a function that has say 2 inputs and 2 outputs, or 3 inputs and 3 outputs, is that the 2 inputs are the location and the 2 outputs are a vector. So let's look at an example where this might, let's look at an example that would be simple enough that we could think about this. Let's let our output's going to be a vector. Let me just call it u and v, and our inputs are going to be our location x and y. So maybe we have this vector field. We have x plus y and minus x as our 2 functions. What we could do is we could think about some different locations. Those would be inputs, right? 2 numbers, x and y, and the vector that we get as we output those. So that would be u and v. So let me just think about some locations. Maybe 1, 1, maybe negative 1, 1, or 1, negative 1, or negative 1, negative 1. Those are all possible locations that we might consider. Maybe we could do another one, like maybe 2, 1, or 1, 2, and so on. For each of these inputs, we can use this formula to get the output vector. So let's see, if x and y are both 1, x plus y is 1, and x is 1, so this would be negative 1. There's our output vector. At the location negative 1, 1, x plus y is 0, and negative x is 1. At the location 1, negative 1, oh, the sum is 0 again, and negative x is negative 1 this time. And at the location negative 1, negative 1, the sum is negative 2, and the opposite of x would be 1. So for each location, I'm able to create this vector that has entries u and v. 2 plus 1 is 3, right? X plus y, that's how you get the first entry. To get the second entry, you take the opposite of the x. The x in this case is 2, so its opposite is negative 2. This last input that I chose, 1, 2, 1 plus 2 is 3. and negative x would be -1. So we have here what we call a vector field, because for each location we have a vector. So we're, instead of thinking as a transformation, there's this alternate interpretation as a vector field. Let me show you what we mean here. At the location 1, 1, the output is a vector that says go over 2 and down 1. So we have a vector like this. At the location -1, 1, that would be back 1, up 1, we have a vector that says don't go over any, just go up. So at the location 1, -1, down here, we have a vector that says just go down, and go over none and down 1. At the location -1, -1, that would be here, we have the vector that says go back 2 and up 1. Okay. At 2, 1, over 2, up 1, that's this location, the vector says go over 3 and down 2. At 1, 2, then let's see, 1, 2 is up here, right? The vector says go over 3 and down 1. Applying these points, we see for each location we have a vector. Now, this is important in applications. We could interpret the vector maybe as being a velocity. So for maybe this is the fluid that's in the plane, right? So it's a fluid that's spread out in 2 dimensions and then probably really thin in the 3rd dimension. So we can just treat it as though it's all in the plane. So it's the thickness, maybe the thickness of this. So maybe imagine like you turn on the hose and let the water run out on the floor, and this could indicate the velocity, right, of the water at any point. So the direction and speed of this water that's spreading out across the floor. This seems to be, we could plot more points, but this seems to be kind of curling around a bit and moving out at the same time on this vector. So it's kind of got a little bit of a spin to it, so we could plot more vectors. A lot of times you might want to plot these vectors a little bit shorter than they actually are. Maybe you could rescale them all by the same value so that the link still had meaning, but it wasn't so long that the vectors start to overlap. We can do this same sort of vector field. Oh, before we go on, I should notice that this is a linear relationship. We have, because there are 2 outputs, the matrix would have 2 rows, and since there are 2 inputs, it would have 2 columns, so that it can multiply our vector, our column vector, or our matrix of inputs here. To get the first output u, you take 1 times x and 1 times y. To get the second output v, you just take -x and no y. So this is a linear vector field. It can be represented as a matrix times a vector of inputs.